Thank you very much, Johannes, and thank you for the invitation as well. So let me start by sort of giving a little bit of background about what T-polygons are and why we should care about their classification. So that's the introduction, let's say. And just a word of warning, I mean, in the past, when I've given a talk on OneNote, it's usually crashed about 3 times. So, you know, let's just keep our fingers crossed. I start with a lattice polygon, so a 2-dimensional polytope. So a lattice polygon P is called a Fano polygon if the following 2 conditions are satisfied. So 0 is in the interior of P, and the vertices of P are primitive lattice points. So I guess maybe I should say the polygon is inside a lattice N. That's a Fano polygon. And moreover, what does it mean to be a T polygon? That's if, in addition, for all edges E of P, the length of E is divisible by the height of E. And okay, so now it seems to work. And by length and height of edges, I mean lattice length and height. So if you haven't seen it before, let me just give an example. So let's take this polygon here. This. And so the length of these 2 edges here, this one and that one, is 4, because there's 4 intervals there, and the heights are 1. So that condition is satisfied. And moreover, we also see 0 is in the interior of the polygon and the vertices are primitive. So it's a Fano polygon. And so this edge here has length 2 and height 2, and same for that edge. So again, this condition is satisfied here. So this polygon is an example of a T-polygon. So what are they good for? Well, they appear in mirror symmetry, or one formulation of mirror symmetry at least. So
maybe let me ask just a quick question to clarify. So height, you mean like you have an equation for the hyperplane cutting out the face, and
yeah.
So the equal, like the linear function equal whatever, this is the height.
Yes, so yeah, exactly. So measured with respect to the normal vector to the edge. Yeah, there's a unique hyperplane with that normal vector which contains the edge. Yeah.
Yeah, thank you.
So what we expect is that Fano polygons are mirror to that Pezzo surfaces. And kind of the conjecture goes as follows. So given a Fano polygon P, so we construct a toric variety, and it's not the toric variety associated to a polygon that we usually do, so where we take the normal fan. It's something different. So we take the toric variety defined by the spanning fan. Of P. So maybe let's give the toric variety a name. That's X span of P. And the mirror X to P is a generic Q-Gorenstein deformation of X span of P. So this sounds a bit complicated, but actually it's very easy. So let me just do an example. There we also see what the spanning fan is. So let's take the easiest of all lattice polygons. That one. So by the spanning fan, I mean the fan over the vertices of the polygon. So that's this fan here. And of course, the toric variety associated to that is just P2. And in this case, since P2 is rigid, we don't need to do a QG deformation or anything. So the mirror to this polygon is P2. And notice that if you take the Laurent polynomial x plus y plus 1 over xy, which many of you will sort of be more familiar with as a mirror to P2, then how do you pass from one to the other? Well, of course, just by taking the Newton polygon of that Laurent polynomial. But in general, there might be a subtle difference sort of between stating mirror symmetry as a correspondence between Fano's and Laurent polynomials or Fano's and polygons. And I will comment on this a bit later as well. Let's just do maybe one other example, which is that polygon here. So in this case, the spanning fan looks like this. And if you do the calculation, you see that this gives you a singular surface with equation like this inside P3. And in this case, we have to do a deformation to get the mirror. And X in this case, there the mirror was just P2, and here X, the mirror, is a smooth cubic surface. And in general, so the conjecture says the following. There is a one-to-one correspondence between QG families of the Pezzo surfaces and Fano polygons. But I mean, so as stated, this isn't true, of course, because there's finitely many families of the Pezzo surfaces. However, you can easily cook up infinitely many Fano polygons. So we also need an appropriate equivalence relation on the polygon side. And this equivalence relation is called mutation. And I will define that in a second. And then there's also a slight technical point, namely, if a Del Pezzo surface arises from this construction, then by construction, it admits a toric degeneration. Because we started from a toric variety and then deformed to get X. But it just turns out that not every Del Pezzo surface admits a toric degeneration. So the easiest thing is just to sort of put that inside here. So Del Pezzo surfaces of class toric degeneration, sort of, which admit a toric degeneration. And sort of that's as much as I'm going to say about it. There are some other technicalities, but roughly that is the picture. And moreover, so where do T-polygons fit into this picture? T-polygons are a special kind of Fano polygons. And what we expect is that T-polygons should be mirror to families of smooth Del Pezzo surfaces. And if we can verify this, this would be a good test for the conjecture, sort of to see if it also works in the singular case. But of course, that is not a very sort of families of smooth Del Pezzo surfaces. That's not, we've known what they are since the 19th century. So there exist 10 deformation families of smooth Del Pezzos. And so we would really also like there to be 10 equivalence classes of T-polygons up to mutations. And that turns out to be true. And that was proved by Kasprzyk-Nill-Prince, 2015. that there exist 10 mutation equivalence classes of T-polygons. And so you might ask, well, if this has been completely solved, why am I giving a talk about this? And the reason is that the proof of Kasprzyk-Nill-Prince is purely combinatorial. So it works by introducing a notion of minimality on polygons, and then you sort of show that you can reduce every T-polygon to a minimal one. And as such, it seems very hard or basically impossible to generalize, especially to higher dimensions. So the really interesting question would be a similar conjecture in dimension 3, where you look at Fano polytopes and Fano threefolds, and there the same methods just wouldn't work. So a geometric proof is clearly desirable. Okay. Right. So that's what I'm going to talk about. I want to prove that there are 10 mutation equivalence classes of T-polygons. So let me tell you what a mutation of a polygon is. So let P be a Fano polygon. N be the inner normal vector. To an edge of P. And I take F to be a lattice segment, such that F is contained in the orthogonal to N. So let's just do a picture. I can use my color. So for example, I could take this normal vector here, and then I can take my lattice segment to be that thing here. So in this case, I have N is -1, -1, and F is the Newton polygon of 1 plus x over y. That's my starting data. And I define a mutated polygon mut NF of P. And I'm being sort of slightly sloppy because if I wrote down the real definition, it would be a bit hard to understand. So morally speaking, we're removing -k copies of F from P at height k for k negative, and adding k copies of F to P at height k for k positive. And by height here, I mean, again, measured with respect to this normal vector that we choose. So what are the different pieces at different heights? So that is the piece at height -1. Here, that's the piece at height. Maybe I should write it up here. Roughly speaking, that's at height +1, and this is at height +2. So after I do the mutation, I get the following polygon. So I need to remove a copy of F from here. So here I'm just going to get a vertex. Down here, I need to add 2 copies of F, so I'm going to get something quite large. And if you work it out, you get this polygon here. Okay, so that's P and that's P prime. And it's sort of not too hard to show that if P and P prime are mutation equivalent, meaning there's a sequence of mutations from one to the other, then they give rise to the same mirror. That's Pezzo. And also, if P is a T-polygon, then so is P prime as well. So mutation induces an equivalence relation on the set of T-polygons. Okay, so that's all good and well, but so far we've just done combinatorics so far, and I want to give a geometric proof, so now we are going to do some geometry. And for that, we're going to introduce a new player, namely a Laurent polynomial. So from now on, we're only going to focus on T-polygons. So I'm going to fix a T-polygon P and consider a Laurent polynomial f in C x plus 1 x y minus 1 with Newton polygon equal to P. So this polygon P defines a polarized toric variety xp, dp. Now, let me emphasize here, now I'm talking about the usual construction, where a polygon, if you take the normal fan, you get a toric variety. That's something different to what we had in the introduction with the spanning fan. It's a different construction. And if your polygon is reflexive, then the spanning fan of one polygon is exactly the normal fan of the dual polygon. So there is some duality inbuilt there, but sort of for general T-polygons or Fano polygons, these are genuinely different toric varieties that you will get. And now I'm really back to classical toric geometry, where I take the normal fan to my polygon. So via the normal fan. And what is dp? Well, it's the sum over all edges. So each edge gives rise to a toric divisor, and which I call dE. And it appears with multiplicity equal to the height of the edge. And sort of classical toric geometry results tell you that the lattice points of P give a basis of sections for this line bundle. O of dP. Now, in our context, we have two canonical sections. First of all, the Laurent polynomial is a linear combination of lattice points, so it gives us a section. But then we also assumed that 0 is in the interior of the polygon. So the constant monomial 1 also gives us a section. And I denote this constant monomial 1 like this, sort of to make it clear that it's not a number, but a monomial. 1 and f give a pencil of sections of O of dP and define a rational map. From xp to p1, which is just given by 1 and f. Now I want to use this state. So basically what the thing I want to do is now I want to resolve the this rational map. So I define the surface xf by. So the first thing I want to do is this toric variety xp is usually singular. So I want to do a toric resolution of singularities. So resolving singularities of xp to get a smooth toric surface xp tilde. Then the next thing is I want to resolve the base locus of phi to get a smooth surface, not longer toric, xf tilde. Okay, didn't break down. And this surface xf tilde now comes with a map to P1, with a regular map. So don't have any space here. So maybe I can, does this work? Let's see. Okay, I'm not going to spend time figuring out how this works. So I'm just going to draw the same diagram again here. So my xf sits up here and it comes with a map to my xf tilde sits up here and it comes with a map pi to P1. And then finally I construct -1 curves contained in fibers of pi to get a relatively minimal surface xf. Just smooth again, of course. So let's just do an example because it's actually quite easy in an example. So let's take our favorite polygon again, that one. So the vanishing locus of the constant monomial has a section of this line bundle associated to this polygon is just the toric boundary. So that's P. And let me just draw the vanishing locus of f. So f is some curve, the vanishing locus of f is some curve in the toric variety, and I'm just going to draw that curve. And now this pencil just interpolates between these two curves. The members of the pencil are just curves in between these two. But however, they all pass through the points where the toric boundary meets f. Because these are exactly the base points of the pencil. So and then, so we immediately see that this is almost a fibration already, except that all of the fibers are meeting at these base points here. And sort of, so to get a fibration to P1, the thing we have to do is to blow up these points, then we replace them with a P1, and this it precisely adds the missing point to each fiber. And this is exactly what this construction is doing. And so the fiber over a point ST in P1 is exactly the curve defined by S plus F times T equals 0. So fiber over fiber pi minus 1 of S comma T is the curve S plus Ft equals 0. Okay. What is this? Okay, I'm not going to draw this again. So, and let me just tell you what happens in this example. So for this polygon here, so it's a fibration of a P1. And also remember that in the first step, we had to resolve the singularities here. And if you sort of do the calculation, you see that these are all a third 1-2 singularities, which means it's a quotient of C2 by third roots of unity acting with weights 1 and 2. So if you blow that point up, you replace it with 2 minus 2 curves. So in total, the fiber over infinity will be a 9-gon of rational curves, 5, 6, 7, 8, 9. And the general fiber will be a smooth elliptic curve. And then you also have some singular fibers, which I think are at -3 omega, and -3 omega squared, where omega is a third root of unity. Okay, and so let me just finish saying what I wanted to say. In this case, we don't have to contract any -1 curves. There are just no -1 curves in the fibers. Okay, let me close again. Let me open again. Let's continue. And this is something that happens in general. So if P is a T-polygon, and F is a Laurent polynomial, with newt F equal to P, then XF is an elliptic surface over P1. So that's what we just had in the picture that has now disappeared. The generic fiber was a smooth elliptic curve. But now also, let's take a slightly different point of view, because there is a distinguished fiber in this elliptic surface, and that's the fiber over infinity, because that's the fiber that corresponds to the toric boundary. And that's some additional piece of data that we're going to use. So let me make a definition. So a Leuinger pair, XD, is a smooth projective surface X with a nodal anti-canonical divisor D. And if you have a smooth toric variety, then, and you take the divisor to be the toric boundary, that's an example of a Leuinger pair. So XP tilde, which is the smooth resolution, is a toric Leuinger pair. And from this, it follows that XF together with the fiber over infinity is also a Leuinger pair. And let me just briefly explain why. So to resolve the base locus, we blow up points in the interior of the toric boundary. Those are interior blow-ups. And then if we have to construct some -1 curves, well, these are just toric blowdowns. So we construct components of the divisor. And in each case, you will again get a Leuinger pair after you do one of these operations. And the good thing about these Leuinger pairs is there is a Torelli theorem for them. So there exists a Torelli theorem, and that's due to Gross-Hacking and Kiel. And how does this work? So given a Leuinger pair XD, we define the lattice lambda, which is those line bundles, such that if you intersect them with a component of D, you get 0. So here D is the sum of the DIs. Okay? And then we define the period point of XD as a map from lambda to pick 0 of D, which is isomorphic to C star. And it's defined as follows. We take a line bundle and we just restrict it to D. So that's a simple looking definition, but maybe it's not really intuitive what's going on. So let's do an example. So I'm going to start with P2 with its toric boundary. So it's triangle of lines. And I'm going to construct a Leuinger pair XD by blowing up a few points. So I'm going to blow up once at lambda1, once at lambda2, and twice at lambda3. Okay, and let me label these exceptional divisors. Now we see that both E1 minus E2 and E4 are elements of that lattice. So this condition is satisfied for both of these classes. So let's just compute the period points. So if I restrict the line bundle E1 minus E2 to D, I get O of lambda1 over lambda2. But if I restrict the line bundle of E4 to D, well, E4 doesn't meet the divisor at all. So I just get the trivial line bundle. So there are two takeaways from there. And the first one is the period point roughly tells us the location of the blow-ups. And the other thing is, the reason this element is in the kernel here is because we made a non-generic choice of blow-ups. Because generically, we would have blown up 2 different points along the divisor. But we did something non-generic. We blew up twice at the same point. And this created an element in the kernel of the period map. So the less generic the blow-ups, the larger the kernel of phi x. And sort of this is a bit imprecise because, of course, this toric model isn't part of the data of a Loinger pair. So there we made a choice. We choose a toric model. You can always do that. But if you want to prove anything about these things in general, you always need to fiddle around a bit. But for me, that's sort of kind of the intuitive reason, sort of what the period point is really measuring, sort of. And what does the Torelli theorem say? So that's the theorem due to Gross-Hacking and Kiel. In a family of Loinger pairs, the period point determines the pair up to isomorphism, and also any period point is realized by some pair. So the period map is surjective. And in a way, this theorem becomes a bit obvious if you look at this picture, because if we believe that the period point sort of roughly tells us the location of the blow-ups, then all the Torelli theorem is saying that if you know the location of the blow-ups, you can reconstruct X. And that's obvious because you can just then blow up these points and you get X. Of course, there are some subtleties in there, and it's not as easy as that. But roughly speaking, it is sort of morally speaking, rather, a family of Loinger pairs, you get that by moving around the points you blow up. Sort of that's what happened. That's what gives you the moduli of these Loinger pairs, by moving around the points you blow up. And then the period point just gives, and the Torelli theorem just tells you that if you blow up at the same points, then of course the surfaces are isomorphic. Okay, so let's go back to our surface XF. Okay. So remember that XF was an elliptic surface. So the divisor, which was the fiber over infinity, has strictly negative semi-definite intersection matrix. And in English, this just means the following. So I'm going to abbreviate this as SNSD. i.e., D is either a cycle of -2 curves or an irreducible nodal curve. And the reason this is true is we know that from Kodaire's classification of singular fibers of elliptic surfaces, that every reducible fiber, all the components have self-intersection -2. So that comes from Kodaira classification. Now we could ask, well, can we classify certain family of Leuinger pairs if we assume that D is a cycle of -2 curves or an irreducible nodal curve? And the answer is yes, we can. So that's a theorem which is original due to Friedman. And it says the following. So there are certain number of deformation families of Leuinger pairs XD with D strictly negative semi-definite. And I mentioned the number 10 at the beginning, which is the number of families of their Pezzo surfaces. And of course, that's where this number comes from. So there are exactly 10 deformation families of these Leuinger pairs. So let's just recap what we've done so far. So we started with a T-polygon. So take a T-polygon P. Take a Laurent polynomial F with newt F equal to P. And this gives us a Leuinger pair XFD with D strictly negative semi-definite. And so by this theorem, XF, D is a member of one of these 10 families. But now we want to use the period point to pin it down even further. And notice that we've got some degree of freedom here because I just chose some random Laurent polynomial with Newton polygon equal to P. So maybe if I make a certain choice, I can say something more. And it turns out there is a canonical choice of Laurent polynomial. There exists a canonical choice of Laurent polynomial. Namely, the unique normalized maximally mutable Laurent polynomial F with newt F equal to P. And so let me just very briefly tell you what this means. I'm not going to define it. I'm just going to draw a picture. So if you've been to any Fano search talks, then you might have heard these words, or even by Al. And sort of the coefficients you have to assign to your Laurent polynomial are binomial coefficients along the edges. 0 at the origin, and it turns out here you have to put 8 for this Laurent polynomial. And if I draw the 0 locus of F, it looks as follows. And so we see that this Laurent polynomial is very non-generic, these coefficients here. Because if you take a random Laurent polynomial, you would expect it to hit that edge at 4 different points. But here, all of these 4 points are squished together at this point with tangency 4. So if you resolve the base locus of the pencil and you blow up, you actually need to do 4 blow-ups here. And so this will give you a very large kernel of the period point. And so it shouldn't come as a surprise that if F is normalized, maximally mutable, I abbreviate like that, then actually the period point has maximal kernel. So it's constant equal to 1. Can you still see?
Yes.
Okay. XF is constant equal to 1 if F is MMLP. And now we're in really good shape because in each of the 10 families, so the 10 families of this theorem here, there exists a unique pair xi, di with period point constant equal to 1. by the Torelli theorem. And it follows that our pair xfd has to be isomorphic to xi di for some I between 1 and 10. And it actually turns out that each of these xi di's arises from a T-polygon by the construction sort of described before. From a T-polygon, pi with maximally immutable Laurent polynomial fi. So we have the following diagram. So we have xf, which is isomorphic to xi at the top. Then we construct the xf by blowing up a bunch of points on the toric variety xp, and xi is constructed by blowing up points on the toric variety xpi. Inside here, we have a dense torus, and inside here, we also have a dense torus. So we have a birational map here. The phi is a birational map. Sort of, it's just a composition of going around this diagram. And it satisfies, if you pull back the Laurent polynomial here, you get the Laurent polynomial here. And it's volume preserving, where sort of it preserves the holomorphic volume form on the torus, which is given by dx, which dy over xy. And the reason for that condition is that we're only ever blowing up on the boundary of these toric varieties. So we're never blowing up in the interior of the torus. And so what we want to show is that P is mutation equivalent to the PI. And I'm going to give it a different name. I'm going to call it Q. And I'm going to define, sort of, just to make the notation a bit easier, the maximal immutable Laurent polynomial associated to PI. I called it Fi, but now I want to call it G. Now, we're almost done. So that what we need to do is we need to factorize this birational map phi into what are called algebraic mutations. Let me very briefly define what I mean by an algebraic mutation. Fix a lattice n, a vector n in n, and a Laurent polynomial such that the exponents are orthogonal to n. And consider the automorphism from the function field to the function field that sends a monomial x to the m times f to the power n inner product with m. So the induced birational map mu n f from the torus of n to the torus of n is called an algebraic mutation. And if I take a Laurent polynomial, I could ask, well, what happens if I pull back f along this map? In general, if you pull back a Laurent polynomial via a birational map, you just get some rational function. But if it turns out you do get a Laurent polynomial again, then you call this Laurent polynomial mutable. So it's mutable with respect to mu uf. Need to check this every 2 seconds. Mutable with respect to uf if mu star uf of f is a Laurent polynomial again. And it might not come as a surprise that actually, so if f is mutable with respect to u and f, then the Newton polygon of f is mutable with respect to u and newt f. And if you remember from before what I meant by mutations of polygons, it was something about removing copies of a line segment and adding them somewhere else. And this is kind of what this factor here is doing. So this inner product here measures the height of a monomial with respect to the normal vector n. And according to whether this height is positive or negative, I need to remove or add copies of f, i.e. multiplying with this Laurent polynomial. And now comes the big proposition, or rather the theorem. So let phi be a volume-preserving birational map. Then two things are true. So phi factors as a composition of mutations. Phi 1. Okay. Haha, that's what's happening. Phi 1, where each of the phi i's is a mutation, algebraic mutation. And moreover, fk, which I define to be the pullback along the first k of these maps of f, is a Laurent polynomial. And I should note, actually, the first part of this theorem was already known. So the part 1 was proven by Jérémy Blanc already. So that it factorizes into mutations. But I also need this property that if you pull it back, you always get a Laurent polynomial at each step. Actually, I forgot a condition here, volume preserving and g, f and g such that, important point. Yeah, so I take a birational map and two Laurent polynomials such that the pullback of f is g. Then I can factorize phi into mutations such that if I pull back f along phi 1, I get a Laurent polynomial. Then if I pull back along f2, I get a Laurent polynomial again until I get to g. So, i.e., in other words, fk is mutable with respect to phi k plus 1 for all k. And now comes the punchline finally. So we have our map here. The map from here. We know that f pulls back to g, and it's volume preserving as well. Now I factor it like this. So I have my first torus here. So I guess I should draw it like this. Phi n. So this gives me a sequence of mutations between f and g. So from f to f1 to ... up to fn, which is equal to g. Because at each step, I know that phi 1 is a mutation, f is mutable with respect to that one, then I define f1 to be the polynomial I get there. And every step I do this, and so I can mutate from f to g. And now I just take the induced mutations on Newton polygons. From P, which was defined to be the Newton polygon of f, up to the Newton polygon of G, which is Q. So we've shown that P is mutation equivalent to Q. And Q was one of the 10 reference polygons we started with. So summarizing, we started with any T-polygon, P. We constructed this surface XF. We showed that this XF has to be isomorphic to XI for some I from 1 to 10. And then we've shown that this implies that P must be mutation equivalent to the polygon of this surface. Here, so Q was the polygon to the one surface that this is isomorphic to. So this completes the proof, and I think I should stop as well because it's 11 o'clock.